started. So 7th and final session of this E-Lecture Series, and I am delighted to introduce Professor Shaun Watmough, who is the Director of the School of the Environment at Trent University. Biogeochemical cycling of both natural and anthropogenic elements. Phosphorus, nitrogen, among others. He has developed novel isotopic techniques to advance our understanding of metal cycling, and he's also evaluated a number of models, including those that are used to predict the effects of acidification. He's published extensively on metal biogeochemistry and on the effects of both acidification and more widely climate change. So following on from our two sessions in the last few weeks on risk assessment, today Shaun is going to present some case studies for retroactive and proactive soil risk assessment. So I'll pass over to Shaun.
Okay, thank you, Margaret. Just let me check here. Okay, can everybody see the screen? Can you all hear me?
Yeah, we can all hear you.
Good.
Fine, yeah.
Okay, so this is my, it's always strange talking to a screen because you don't know if anyone's actually listening. But good morning, good afternoon, good evening, good night, depending on where you are and listen to this, this talk I'm going to give. Because it's, I believe, the final lecture in a series of lectures that you've had. What I decided to do is kind of just go through risk assessments. You're going or highlighting two specific cases that I've been involved with, and the reason I chose to do that is because what I hope the take-home message from this series of lectures is that while we can learn techniques and applications, ultimately every case that we look at is different. And when you go into a specific case, you've got to look at its unique features and you've got to design the study accordingly. So it's kind of a way of bringing things together, I suppose. Hopefully, I'll talk slowly enough. My accent is not Ontario. You may have guessed it's from Northern England. But hopefully you will understand what I'm going to say. So the two case studies I'm going to talk about, one is in Sudbury, Ontario, which is actually the reason I came to Canada a few years ago. I'll just say a few. And it was a very, very heavily impacted mining area that is showing signs of recovery. And I'll talk about a risk assessment that was done there. And in that case, I was a reviewer of this, and it was the most expensive risk assessment done in Canada. Soils risk assessment. And then the other one is one I was involved in doing, which is more recent, out in British Columbia, and that's where we're actually trying to evaluate the potential risk. So it's quite different. One is looking at retroactively, you know, we've devastated the landscape, is there still environmental damage? And the other one is saying, well, will there be environmental damage? And we have to do it, even though conceptually it's the same thing, we're trying to protect the environment, we go about it in different ways. So I thought I'd talk about these two studies. Just let me. Okay, so just you may have seen this, but just it's a good point of starting here about a risk assessment. It's a tool that's useful for estimating potential adverse effects that can arise from contamination at a site. And importantly, it informs policy decisions in terms of, you know, is it okay? Can we just leave it alone? Or what should we do? And in both the cases I'm going to go through today, the outcomes were different, and the policy, the management decisions were different because of the findings of the risk assessments. As you'll see in this little image here, I'll use my little mouse here. Well, I'm going to talk primarily in this area here, and you see the text is, you know, problem formulation. So formulation means you have to think about it. You can't just go there. You can't just take something off a shelf. You can't take a textbook. You have to sit through it and go through a thought process to make sure that you are actually measuring the right things, the right time, and actually putting the information together. It's important to communicate these to whoever's in charge. You'll come up with some sort of management that can feed back into the risk assessment to actually see if you're doing something correctly. So while there's a general framework, the specifics are all, it's a black box, and we have to teach each case separately. And the reason we do risk assessments is most regions of the world, we have standards. We have criteria, whether it's water, sediments, soils, that trigger some sort of response. And these are generic criteria. But these criteria, by necessity, are very conservative. So I won't go into how these criteria are developed, but essentially they compile information, publish information. Sometimes government agencies will do their own studies. And you're basically looking at like a lowest effects level or some version of that with a view of saying if you're above this guideline, then there's a potential for damage and something has to be done. Now, in some cases, it has to be remediation efforts. You've got to move the soil, you've got to treat the soil. In other cases, it might trigger a risk assessment. So that's the reason we have risk assessments, because these criteria say there's potential for damage. It does not say that there is damage. So the problem with general criteria, there's more, but I just identified 3 here, is that they vary by agency. So whether you're in Europe, whether you're in North America, US, Canada, even different provinces have different soil standards, soil criteria. And that just shows that, you know, these values that you see are not fixed values. They're not linked definitively to harmful effects. They are guidelines to be protective. And so depending where you're in the world, you've got to find the appropriate ones. They vary by use, and that doesn't mean just whether it's groundwater, potable water, sediments or soils. If you look here, for example, let's look at arsenic. If it's agriculture, the standard is 11 micrograms per gram parts per million. If it's residential, then or commercial, then it's 18. And the idea being is because we're growing food here, we want lower standards than if we're not growing food. So a lot of variability. So it's not just one general number. It's applied to different situations, and these numbers do vary. And finally, most important is they are very protective. They have to be, because it's the first line of defense we have when protecting the environment. If we do not set our criteria to be protective, then there's risk that we can have environmental damage and we have no mechanism to protect the environment. So it's the first line in the sand. It does not mean harm. It means we have to look more into the situation. And so when we're doing risk assessments, I'm going to talk about ecological risk assessments, which is where we're attempting to estimate and quantify, if possible, the risk to the environment and the non-human inhabitants. In both cases, and I'm not going to talk about it, in both the risk assessments I'm going to talk about today, there was also a human element to it. So in both cases, there was a human risk assessment done as well. It wasn't just an ecological risk or a soils risk. There were other aspects considered, and in both cases, there was a human risk assessment done as well. And it's, you know, again, conceptually it's similar in terms of we formulate a problem, we do the assessments, but obviously the way we go about it is quite different. So, you know, ultimately, when you're doing these risk assessments, and ERA, there is an environmental risk assessment, we do have a framework that we can follow loosely. Doesn't mean that each one is done the same, but I think if you can remember these 4 steps, then you're going a long way towards actually coming up with the right way of doing a risk assessment. The first one is you've got to have your receptor identified. If you look out the window, if you look outside in the environment, There are millions of species, millions of, what is it that you're trying to protect? That's key, because you can't go out there and assess the risk to everything. It's just too vast. So you have to narrow down, and you have to make sure that whatever you're choosing as a receptor adequately captures the aspects of the environment that you are concerned about. So that's a very important step, and I'll talk a little bit about how that's done. The next step is the exposure. So once you've got your chemicals of concern, what's the level of exposure that your receptors are receiving? You know, so if we're looking at animals that are migratory, for example, they're not in that environment the whole time. Are they living in water? Are they in sediments? Are they getting a lot of air? Are they actually? So the exposure is difficult to estimate. It's often done through modeling to try and estimate the amount of contaminant at a daily level that that the receptors are receiving. The third one is the hazard. And so, and this is why it ties back into the number one. You've chosen your receptor, but you have to have some idea of what's the level of the chemical concern that actually produces some impact on that receptor. And that's the hazard value. So in some cases, it's a bioassay, in other cases, it's a study, but you have to come up with some sort of endpoint that you know the chemical of concern is impacting that receptor. And then ultimately, to evaluate the risk, you're looking at the exposure and you're looking at the hazard, and you're identifying whether the exposure is likely to exceed the hazard, the likelihood, and you'll then from that determine the level of risk. So that's in simple terms. And I should point out that oftentimes the end product of these risk characterizations is a very simple red, yellow, green flag. Because there's a lot of complicated information goes into this, and a lot of these go to public, for public conception, because oftentimes it's the public who are interested in these kind of things. So if you make these things overly complicated, people don't understand, and that leads to concern. So you try and simplify as much as you can your findings, such that anyone with a reasonable amount of intelligence can understand exactly what are you talking about, what you've done, and what the risk is to the environment. So that communication is key. And in the second case study, there were some problems that arose from the risk assessment, mainly because of the way the government communicated it to the public, and there was kind of went to courts, and anyway, it all worked out in the end. But it is important to get the communication piece right. So that's a little bit of background in terms of risk assessment. I'm pretty convinced that you've done some of that before, so it's just a kind of a refresher before we get onto the crunch of this this talk. So Sudbury, the Sudbury Soils Risk Assessment. So just to orientate you, this is Ontario in Eastern Canada. This would be New York, Pennsylvania down here, and getting to the Midwest. Toronto is right here. I'm right here in Peterborough. Originally, when I came to Canada, I thought I would just nip up to Sudbury on a day, and it's about 5-hour drive from Peterborough and Trent to Sudbury, and it's a unique geological feature. Basically, a meteor hit millions of years ago, so the geology is quite different. It's a very rich ore body, nickel, copper. Over 100 years of mining and smelting. So in the old days, if you look down here, so prior to about 1930, they used to smelt the ore with a roast bed, and that's just a clearing in the forest. It's about 1 kilometer long, about 50, 60 meters wide, and they would line timber. So the forests were cut down, which is important. They cut down because originally wood, the fuel. They put the wood down, the metal ore, stacked it about 30 meters high, and then set fire to it. And that, what you can see there is the fumes, and it would burn for several weeks, and they would collect the molten ore, and that's how the original smelting went on in Sudbury. And you can still see these scars in the landscape, these roast beds. The biggest one, which is what this one is, it's the O'Donnell roast bed. And I've talked to people who lived when this was operational, and they told me stories about the men having to sort of fall down on their stomachs because they couldn't breathe because of the fumes. The school was about 1 kilometre away, and sometimes classes were cancelled because the winds changed, and this went over the classroom. They couldn't see the chalkboard. But anyway, in the sort of 1920s, 1930s, I think the O'Donnell closed in 1929. They went to smelters, and ultimately in the mid-late 70s, they built something called a super stack, which I'm sure you've heard of. It's the largest stack in the world, and it's the main smelter emission. So originally it was dilution as a solution. Taller stack, further the emissions spread. So for the same amount, you're distributing it over a larger area. So you're lessening the environmental impact, certainly locally. But also they did develop a lot of new scrubbing technologies. So emissions have gone down dramatically in Sudbury over the last 30, 40 years, about 95% reduction in SO2. And also the two main companies that are operating in Sudbury have done a very extensive liming. That's what you see here, liming study, replanting scheme. So there's been a huge change in the landscape, going from this, trying to get back to something natural. So that's the brief history of Sudbury. It is a very heavily impacted landscape. There's two Google images here. This was in the 80s, this is more recently. And you can just see in terms of the amount of degradation, these are all barren lands, tailings. Basically, what happened was, obviously, if you go back to the roast beds, the vegetation, the trees were cut down. These soils are very, very shallow. They're often less than 1/2 meter over bedrock. And so when you cut down the trees with the high sulfur dioxide, you couldn't get vegetation reestablished. You got a lot of erosion. So you ended up with a lot of bare soil or bare rock and very thin soils. And then now with the replanting, replanting, we're starting to get better. So it's recovering, but it still remains quite degraded if you drive around there. So it's still visibly a very impacted area. And so in the early 2000s, the Ontario Ministry of Environment did a scoping study, and they basically separated out Sudbury into different zones, and they measured for a suite of metals, so arsenic, cobalt, copper, lead, nickel, selenium. So nickel, copper, cobalt are the three metals that are primarily associated with the smelting, but you also got a lot of lead because there's a lot of fuel used, and arsenic as well. And they had sites, and so remember I talked about criteria depending on use, so area. So we've got residential, we've got schools, daycares, we've got parks, and then we've got, you know, a number of samples, 184, 45, 95. So these were all surface soil samples taken 0 to 5 centimeters. And if you just look at the mean value, so in the residential areas in the Sudbury core, the average was 10, the guideline is 20, but some values did exceed the guideline. Cobalt, the average was 18, so the guideline is 40. Again, a few samples exceeded the guideline. But once we start to get to copper and nickel, you'll see that the average is almost 400 parts per million, whereas the guideline is 225 in Ontario, and some almost 2,000 parts per million. And then with nickel, again, the average is 400, whereas the guideline is 150. So basically, they exceed the generic criteria. So that meant something had to be done. Now, the problem is that Sudbury's and the impact, there's historically in the number of smelters, which is why you can see this bubbling shape here. It kind of reflects the location of the smelters in the Sudbury region. So hopefully the colors show. So if you're looking at the yellow here, which is the guideline, 150 parts per million or micrograms per gram. And if you look down here at the scale, so 10 kilometers, 20 kilometers. So this is about 30 kilometers this way and about 30. So we've got about 900 square kilometers that exceed the provincial guideline. So what happens? That was the starting point. So this was the government's findings in 2000, and this is what led in to the risk assessment, because the mining companies that just to treat that much area, soils, or bring in fresh soil to try and would be extremely expensive. And as you remember, these criteria are generic. Doesn't mean it's actually having an environmental impact. So that's why a risk assessment was done in this case. And so basically they were done on a number of metals but that were associated with the smelting activities. The risk assessment was determined in the Sudbury environment was an unacceptable risk. And that's an interesting or an important point. There are stakeholders. And so as a scientist, our job is to collect information and to present it in an impartial way to all stakeholders. And then the decisions are made by other people as to whether that is an acceptable risk or not. We don't determine that it is acceptable or not acceptable. We give the information, we say the likelihood of damage, and then some people might say, well, if it's only going to damage a small area, it's okay because it's going to employ this many people. It's going to bring this much money into the region. So you need to separate those things out in terms of who's defining the risk. That is done by the managers, the policy people, who take into account all stakeholder interests, not just the environmental people or industry people or indigenous communities. It may be a bunch of people involved. The chemicals of concern that were identified based on that screening that exceeded the criteria were copper, nickel, arsenic, cobalt, selenium, and lead. And for a chemical of concern, it's got to be associated with smelter activities and present across the study area. So the way the risk assessment was done in Sudbury, there was kind of three objectives. The first one was to evaluate the extent to which those chemicals of concern. They also added cadmium because of the concerns over cadmium toxicity and the fact that it was identified to be high in some areas, preventing the recovery of regionally representative self-sustaining plants. So this is, in terms of if you go back to the beginning, I gave that little sort of the 4 steps. This was trying to identify the receptors. So this is a little bit different. There were 2 kinds of receptors. One was just plant communities. And when you were doing the plant communities, you weren't really doing the traditional exposure hazard risk formulae. You had to look at the functioning of a terrestrial plant ecosystem. So that was kind of, the first question was kind of done in its own right. Is there an impact to these plant communities? Are they functioning? And then number 2 and number 3 were done through the traditional risk assessment, where traditional or terrestrial wildlife populations, certain species were chosen and they were evaluated through traditional methods where you estimate the intake of these chemicals, their exposure, and then you compare it to what the reported literature values are for risk. And from that, you'll estimate whether there's a potential impact on these on wildlife. And then also they want to identify whether there are any specific species that are endangered. Again, you just don't choose your receptors randomly. You have to think about your receptors. And if you're in a specific area that is home to a unique species, then you've got to consider that species. It gets put to the top of the list. And so one thing that happened is when you're going through the receptors, you also choose species that may be rare or endangered. So there was kind of 2 parallel things going on. One dealing with vegetation, which was number 1, and number 2 was 2 and 3 were dealing with animals. So in terms of the first one, what happened is 18 sites were chosen in the Sudbury region, ranging from the core, where it was quite degraded visibly, to reference sites or control sites away from the immediate impacts of the smelter emissions. With the idea of, by having reference sites, because forests vary naturally in their function. If you've got different soil type, if you've got different vegetation, you're going to get different functioning. So you try to standardize as much as you could what you would expect to be present at a degraded site, and everything is compared relative to your reference site. So 18 sites were studied, and a suite of soil, physical, chemical data. There were soil toxicity tests done, there were plant surveys done, and there were decomposition studies. So quite basic tests done. A decomposition study is just you collect leaves from that area, you put them into a fine mesh bag, you leave them out there, and you see how quickly those leaves get broken down. It's a way, indirect and a very easy way of assessing microbial community without getting too technical. It's something, because it's really, if you were to start looking at microbial communities, things can get really complicated. Lots of species, lots of diversity, and really what we're interested in is not so much diversity of microbes, but the functioning of these systems, not necessarily the, I think that would start to get a little bit more complicated. And this is an image actually from the same, taken 30 years apart. It's the same site, and it shows the regreening that occurred from mid 1970s to the 2000s. In terms of 2 and 3, the receptors, it's a process of identifying the ecological receptors of concern, and you'll often see these known as VECs, valued ecosystem component, and that's what you want to protect. So the way this is normally done is you get, or it should be done ideally, is you get all the stakeholders who are interested in a room, and you try and hash out a list, and you're trying to take into account things like, you know, does data exist on these species that you can estimate the hazard with? If you choose something that is completely you know, unknown, it's very hard to know what the critical level is for this organism. Is it representative? I mean, you need to think about where it is in the food chain. Its functioning. Is it something that people are attracted to? Again, it's that that's the, you know, I mean, people generally don't like frogs, perhaps, but they might like certain types of birds. So those things, so, and if you look outside, there's many species you could choose, but you have to narrow it down to a group of organisms that you can actually deal with. So even though this was a, you know, one of the largest risk assessments done, you start to narrow down the VECs such that I think there's about 10 or 12 VECs that were chosen as part of this study. And here they are, and I threw some pictures in just in case people don't know. It's Canada there, so I put the beaver and the moose. But if you look at the species, they were chosen for a reason. So we have shrew of all here, so low on the food chain, interacting mostly with soils and vegetation. So they're our first step. Then we have moose, white-tailed deer, again, so feeding directly on vegetation. Also, in case of moose, it's something that's very important to the indigenous communities and many locals. People are attracted to deer for many reasons. You've got some carnivores, so in terms of red fox. So the idea is if you're getting bioaccumulation or biomagnification, you've got them covered. Beaver, linking terrestrial to aquatic systems, so you've got a water. And then you've got 2 bird species chosen, robin and ruffed grouse. It's right here. And finally, this was the only rare or endangered species that was identified in the Sudbury area, the peregrine falcon. So with respect to objective 3, it was the peregrine falcon that was chosen. There was no other rare, in this instance, no other rare species. So when you're dealing with the exposure assessment, you know, you go through these 5 steps. What are the chemicals of potential concern to be assessed? So we'd already talked about that. We identified that we had copper, nickel, cadmium, arsenic, cobalt, and selenium. And then what you're doing then is you're using information. So what are the pathways by which these specific VECs, the valued ecosystem components, are exposed to these chemicals? So are they coming through water? If they are, you need to know what the concentrations of the metals in the water, how much water these animals take in, and from that you can estimate their dose. Are they just breathing it in? So you need to estimate of concentrations in dust in the air. and then some estimate of how much they will be exposed to. Either again, things directly from the soil or from plants. So as you can see, a lot of these things are basically done by having some basic information on these aspects, and you're using models, and you're always being conservative when you're going through this process. You are trying to use, you're trying to be protective in this environment. So when you're going through this and you have a range of values, you will typically assume the highest value that you've measured, because that's what's out there. Same with the earth, same with the soil. What is the magnitude of this potential exposure? So basically, once you've got the pathways, you actually calculate the amount of exposure against the minerals, and frequency. In some cases, this exposure is not 24 hours. Through the air it may be, but not through soil. So you need some way of standardizing the exposure to try and get a daily, weekly, monthly, annual exposure that you can then tie into how much of the chemicals are concerned are entering these VECs, such that you can evaluate the potential risk. And the hazard assessment is basically, for the most part, going to the literature, and you don't necessarily have to have the same species. So, for example, if you've got shrews or voles, oftentimes a lot of studies are done on rats, and you just transfer the information. So, if it's close enough, you can transfer that way. And again, that ties into your choice of VECs, that you have information that you can use. And the hazard assessment is the process of determining the potential for specified contaminants to cause adverse effects in the exposed individuals or populations, and of estimating the relationship between extent of exposure and the severity of extent. So, as I said, ultimately what we're doing here is we're simplifying it. We don't actually know. We're not going out in these risk assessments and finding dead animals or finding animals that are limping around and showing obvious signs. What we're doing is we're estimating their exposure to a chemical based on the literature. We're estimating, is there a potential for this to be damaging? If it's well over the hazard level, then we've got a high confidence level that there will be some damage. If it's approaching that level, then our confidence becomes a little bit less. So we're making a judgment call on how confident we are as to whether there is a potential for environmental damage. We're not actually finding environmental damage per se. So the endpoints for the vegetation, going back to objective 1, was this self-sustaining forest ecosystem. So the 18 sites, they were surveyed and assessed and compared to reference sites to see whether they looked like a normal forest. That was one criteria. Blueberries were identified to be very, very important for both local and indigenous populations. So we looked at the people doing this, looked at blueberries, whether they were able to grow, survive, looking at the berry concentrations, etc. The soils is key. So they looked at soil and little biota, did some bioassays, so growing test plants in the soils to see, look at root growth, etc. Looking at litter decomposition rates to assess the functioning of the soils. And then for the plant, for the objectives 2 and 3, it was looking at the wildlife population. So, so you've collected a lot of information. Ultimately, you have to simplify it. And so, what happens is, in terms of, we use something called the weight of evidence approach, such that we collect a lot of information, and we, I say in this case, and commonly we'll just assign 1 or 3 colors. If it's red, that means that we're pretty sure that is an impact and it's quite harmful. If it's yellow, that means either, we're less certain that there's going to be an impact, or the impact is not quite as severe. And if it's green, that means we don't think there's an issue at all. And so in terms of the sort of the plant communities, so C1, C2, C3 would be different sites. So in this case, we have the plant community was very, very impacted. It was very unlike what we saw in the reference sites. So it was red. It was clearly not a functioning ecosystem, plant ecosystem. Toxicity tests, so when plants were grown in these soils, they did not grow well at all compared to reference soils. So they were also red. In terms of soil characterization, the metal levels themselves weren't greatly elevated. So in that case, it was a yellow color that was assigned. The linear decomposition was very much impaired compared to reference sites. So you had, in this case, we had 3 reds and 1 yellow. So for that site, it gets given a red. It's a weight of evidence. There was 3 reds, 1 yellow, it's a red. If you look at site C2, similarly, the vegetation and plant communities were impaired. It was given a red. But in this case, the toxicity test, the plant growth, they were slightly impaired, but nowhere near as severe as this, and only a little bit less than the reference, so it was yellow. Similarly, the metal levels were not extremely elevated, so yellow. And decomposition was not greatly impaired, but it was slightly less than the control, so it also got yellow. So yellow, 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 1 red, overall risk is yellow. Finally, C3, I think you know by now the way it's going, so plant community was yellow, toxicity and soils were green. They were no different to the reference sites. Decomposition was yellow as well. So in this case, we have 2 yellows, 2 greens. We want to be conservative though, we want to be protective of the environment, so this gets a yellow score. So in this case, we have 1 severely impaired site and 2 moderately impaired sites, even though aspects, there was no impairment. Again, a risk assessment has to be protective. If you were to look at then this in the scale here, so these were the 18 sites, and how they were ranked, and effectively all the sites were either severely impacted, i.e. red, so these are all red sites, or yellow, and these were moderately impacted, and this is the Sudbury core here. So you can see that there's a large area where the plant communities were heavily impacted. However, that was really it. So in terms of just summarizing with the objectives here, so this was objective 1, evaluate the extent to which chemical concern are preventing the recovery of regional representative self-containing terrestrial plant systems. Plant communities in the Sudbury area have been and continue to be impacted by metals in soils. It's quite clear. Terrestrial plant communities are impacted by soil erosion. If you remember, I talked about the erosion that occurred. That in turn has led to low nutrient levels in soil, very low organic matter, and the soils are very acidic. So there's definitely impact on the plant communities. However, the wildlife, I didn't go into that much because really through these hazard assessments or exposure and hazard assessment, there was no evidence that there's any potential risk. There was the only thing that came out of this was basically the lack of the impact on the vegetation can affect habitat. It can affect habitat quality by loss of the forests. It's different habitat, and that will obviously impact the species that are there. But it wasn't the soil contamination or water contamination per se that was having an impact on wildlife. The one endangered species, peregrine, I said there was very few recognized endangered species, and there was no evidence that chemicals of concern for the smelters are having an effect. So these were the 3 objectives. And then what happened, the outcome of this was then basically a follow-up study was proposed, and actually, so the industry had to do that, where they looked at wetlands and aquatic systems. This was a soil risk assessment. It focused purely on upland soils, and there was a belief that wetland soils had been underestimated, and there's no aquatic system. So this led into a following study with looking at wetlands, which I was involved in actually, looking at the wetlands and the aquatic systems. But based on this, the government decided that no remediation efforts on the soils over and above what was currently being done with the liming and revegetation mainly because they thought that the wildlife were not being endangered by the metal levels. And if you could get back the vegetation, then you would get the wildlife back. But a lot of it was through past activities and not present activities. So trying to get the soils back, organic matter was the key thing. So that was my retroactive risk assessment. I want to quickly go into my proactive one. I don't have much time, I just realized this. But just to show you that it can be quite different. This is a pristine area, just from the photograph. We want to keep this area pristine, very different. The problem is there's an aluminium smelter in Kitimat, and it's requesting a permit to increase sulfur dioxide emissions to 42 tons per day. They had a permit for 28, and they wanted to go up to 42. And the question was, will this increase have an impact on the environment? So the study area is in BC. There's a British Columbia down here. It's on the coast, deep harbour coast here, where they bring in the ore. The smelter's just down here. It's a valley. So the emissions go down here, and it's characterized by these little small beautiful lakes. It's an alpine region, all these mountains, and it's forests. Really recreationally, it's wildlife. It's a very different environment to Sudbury. The risk is that this was the pre-modernization deposition, the one they had the permit for. So the heavier depositions where it's red and yellow, lower depositions purple, and the modeled change is that we're going to get this much larger plume, and we're also going to get more red and green and blue. So that was the concern. We sat in a room again, and we went through this thought process where we kind of talked about emissions. It's going into the atmosphere, that it can potentially impact humans, that it can impact lakes, that it can impact SO2, can impact vegetation directly. But what I really want to focus on here is the soils. The idea is that you can have acid deposition impacting soils, acidify soils, and lead to degradation of the upland forest. So that was one of the receptors that was chosen. So we had humans, we had vegetation, we had lakes, and then we had soils. And so we simplified this to the 4 receptors here. So we have a source, emissions, 42 tons. The SO2 can have direct exposure to people or plants, or it can be indirect through acid deposition and acidification, can impact soils and lakes. So we'll just focus here now. It's not happened yet. It's something that will happen in the future. So we had to use a model, in this case it's a critical load, where we can predict the risk from this elevated deposition, which involved collecting some field data, some soils data, and developing models. And again, our risk assessment, this red, in this case there's 4 scales. There's red, orange, yellow, green. Red means, serious, major, catastrophic. And if we're almost certain or certain, it's red. And then you get this middle ground where it's, there's consequent, like you have some serious damage. It's possible. So it'd be orange. We're not sure that it will occur. Or it can be, medium consequence, some damage, but we don't think it's likely, and it's green. So again, you get this ranking system based on where you, in terms of this case, the soils will fall. It's going to be red, it's going to be orange, it's going to be yellow, it's going to be green. I'm not going to go through this because it's too much time, but basically you have some soils data, you need to get the mineralogy, you need some supplement. So this is the thought process, how you go about with the field sampling. All this gets put into a model called Profile, which gives you the weathering rate. You then have some other climate data, precipitation runoff. You have a critical endpoint that which is what we think will damage the environment. In this case, it's a base cation to lumen ratio in soils. So then you run the model, get the critical load to see what you get, which essentially estimates how much acid deposition a soil can take without acidifying below this ratio. As soils acidify, aluminium concentrations go up. The more aluminium you get, the more potential for toxicity. So that's effectively what we're trying to measure. We're trying to keep the base cation-lumen ratio below a threshold for potential damage. That's our critical load, and it's very soil specific, site specific. Certain soils have higher weathering rates. That means they can take more acid deposition. You then compare the model deposition to the critical load, and if the acid deposition is higher than the critical load, that means you've got exceedance. So in this case, what we were doing is identifying exceedance and by how much would the site be exceeded, and how much of the valley was exceeded. So in terms of going back to that risk table, the consequence of the seriousness was basically how much area exceeded, and our level of certainty was by how much. So our exceedance was much above the critical load of the acid deposition, was far above the critical load. We're pretty certain that's going to happen. If it's close, maybe. If it's below, likely not. So that's how this information was prepared. So we went out, sampled 51 sites in about 3 weeks. It was strategic because we expected it to be tied to bedrock. Sampling sites were spread around there's 11 different geologies. So we tried to capture all those different geologies so that we could create a map. So that's how we went about doing that. Took don't have time, but we had lots of field sampling. It was a lot of fun. As you see, we're in pristine, so not all risk assessments have to be done in impacted landscapes. They can be done in areas that are actually quite beautiful. So lots of grizzly bears and black bears. It was great. Field notes. Just a point of question when you're out there, make sure you make good field notes. We created our own field sheet, so we have these for all sites, lots of photographs if you need to go back. Another thing that's important is archiving soils. With all the soil samples that we bring back, we label, we have archives now. A lot of the expense is going to these sites. You don't want to have to go back to get some soil to do some follow-up studies. So somewhat underrepresented or under thought process is archiving soils. So whenever you're doing these studies, be sure to archive the soils. It can come in very useful. So the results very quickly. So our receptor in this case for upland soils is the green area. This was the weathering rate that we estimated. So green was higher weathering rates, red lower weathering rates, yellow in the middle. The critical load, so blue is a higher critical load. Green is a bit lower, yellow is a bit lower. This is our deposition range. That was when overlay critical load to see whether the deposition exceeds our critical load. And if you look, that's all there was. That small little bit of yellow, that was the only part of the valley that we estimated to exceed the critical load. And notice there was sulfur dioxide emissions prior to the development. So before the upgrade, we predicted 0.08 kilometers squared were exceeded. This would increase to 1/4 or 0.4 kilometers squared. And our total receptor area was almost 2,000 square kilometers. So a very, very small area, extremely small area, but we are pretty sure that it would be exceeded in that small area. So there we go. So a very small area, but exceeded by quite a way. So we're pretty sure that there's damage. And if you zoom in on here, it's right by the smelter. Not surprisingly, a small amount of area exceeded. So in this case, when you go back to the risk, it wasn't low because we did see some impact. So it wasn't green, or 99% of the area was green. We had a small amount that was acceptable impact, but in need of closer scrutiny, moderate monitoring. This was a very small area. So even though it was just a small area, and you have to be sort of protective, for soils, the overall risk for the soils was moderate. And that led to which is ongoing now, environmental effects monitoring network to confirm that the results of these models are indeed correct, and there actually will be no impact to the other parts of the valley. And I think that's it. I think Margaret's going to take over, but if you want more information on the Sudbury soils, there's a website here, the sudburysoilstudy.com. There was a paper that we published just last year on BC. This also includes Prince Rupert as well. So there's 2 risk assessments done in this paper, and it also includes the human health in other aspects to it. So if you're interested in following more, there's the information. Thank you.
I don't think we can hear you, Margaret. Yeah.
Okay.
Can you hear me now?
Yeah.
Okay. We get rid of that. So, saying that thank you to Shaun. Nations of ecological risk assessment at the very large scale at the heavily impacted sites, and also the whole system approaches that you were outlining to prevent impacts at pristine sites. Do we have questions? Okay, maybe I could start. Just you were finishing off there, but the aluminium smelter, and I just wondered if you know, obviously with the risk assessment you've carried out now, showing that that there's from the modelling perspective that there's not likely to be much effect except in a very localised area. If prior to that there had been consideration of investment into sulphur removal technologies.
Yes. So the reason they wanted the permit was because they upgraded their facility. They changed the technology by which they were smelting the aluminium. That involved changing the source of coke, so they were using a high sulfur coke. But also they could have put in sulfur scrubbers, and this was what led to the public concern. It was just that the expense, it would have been very, very expensive.
Yes.
So because they were already just emitting to the atmosphere, the company didn't want to have to put up that expense for installing scrubbers to reduce their emissions. And so that was really the issue. The public wanted them to spend the money. The company didn't want to spend the money.
Yeah, yeah. Okay, yeah, I thought there might be some issues in there. I can see that there is a question that's come in on the group chat from Ian Oliver. What are the criteria for serious, major and catastrophic consequences?
Okay, so that risk assessment table that I showed you that had that terminology, remember there were 4 endpoints. There was humans, there's vegetation, there was lakes, and there was soils. So from a soils perspective, those criteria were based on aerial extent. So if it was just it became how much area was likely to be receiving acid deposition in excess of the critical load. So for us, you know, that terminology isn't quite as dramatic as it would be for human health, for example. So for the human health, it was the same terminology used, but so for serious would probably be, I can't remember off the top of my head, but people with breathing issues or some sort of issues, and they would be harmed by that. That would be serious. Major would be kind of, you know, most people would be harmed, like feel ill effects, and catastrophic is where people start dying in that level. So that terminology perhaps has more meaning for people, less so on soils. For a soil perspective, it was just the area.
Yes, right, okay. So I think, is there another question coming from Ian here? I assume that the smelter company paid for the soil survey and analysis work. Did you have to tender for this, or was the budget agreed some other way?
Oh, I can be bought. No. So actually, the way I got into this, so the company had actually built the upgrade. They've upgraded the smelter, and the assumption was they were going to get the permit. And then right at the last minute, the BC Ministry of Environment said, hang on, you can't just do this without doing a risk assessment. And so I was contacted by the BC Environment as a way of providing information as to how this should be done. So we met in British Columbia and we talked about it. And this is where that little schematic, that's where we created that diagram. That's just a sketched image of something we put on the board. And then, okay, who's going to do this? And so myself and Julian, who's another prof at Trent, said we can do it. And so we were, so it was a dump through environmental consultant, and we were subcontracted out, but we don't take them. So the way it works is I went out there to show the people how to do the sampling, and we did sampling, but the money was paid into research account at Trent. And what we did is we used that money to pay graduate students. And I have my first one defending in a couple of months to do other stuff that was a spin-off. So more academic. So this wasn't necessarily an academic question as such. It was more an applied version, but we could look at more specific academic questions through graduates. So the money was put all into graduate research, even though we were doing this risk assessment.
Thank you. Thank you. Do you have other questions coming in?
Yeah, Shaun, maybe following up on that, you focused on the soils aspect where there was, very, very minimal impact. But you've got, as you said, you've got your human, you've got your vegetation and water. How do you decide among competition among those various receptor categories, especially if you start to see small effects in each of them in different locations? How do you then sort of add it up for an overall assessment of whether you would grant a permit or not in this case?
Okay. So we don't do that. That's not our choice. So what happens in this case is they were done through, so the risk assessment was done through 4 groups, independent, well, not independent, but we're working together, but 4 different, we focused on soils, Limnitech focused on lakes, Greg Lawrence focused on vegetation, and a guy in Ottawa focused on human health. So each section gets reported the way I did for soils, and that goes to BC Environment, and BC Environment are the ones ultimately who we have a series of conference calls, we have meetings, a public information session, and they're the ones ultimately that make the decision based on, and really these things tend to be driven by human health. So human health would overweigh anything else. So, if you had green for soils, green for vegetation, green for lakes, and it was yellow for human health, it would be yellow. And human health would trump. In this case, human health was green. There was no, outside the actual workplace itself, when you got to the local communities, the SO2 levels were not considered harmful. The problem was the standards that the Canadian Council Ministries of Environment were being updated at the time. And so that caused a lot of problem, because with human health, the endpoint is very, is it a 1 hour of this, 2 hours at that, 10 hours at this? The concentration goes down the longer the exposure. Is it the peak value that's important? Is it the chronic exposure? There's a lot more uncertainty, I suppose, on what those criteria are. And so even though based on the existing criteria, it was given green, it was left open that, if we get more information, it might change. So there is right now an extensive SO2 monitoring program that's been established as an outcome of this by schools, by daycares, in the residential areas close by the smelter, to ensure that the levels are as low. And there's also the uncertainty modeling, the atmospheric SO2 as well. So there is the outcome was, yes, you get the permit, but you've got to do very extensive monitoring.
Okay. Can I take you back to the Sudbury example? And you were talking about the various animals and birds that were identified as being impacted, and then you talked about the chemicals that had been identified, and then the next part was looking at the pathways. Water, air, soil was the most important. Was that a single pathway that was identified for a chemical to a receptor, or?
No, not always. And again, I think in some cases it was a little bit more hand waving. So for a herbivore, for example, the idea is that it goes through the vegetation from the soil. And so you had an estimate of the, and also drink, right? Drinking water. So in that case, they're estimating the volume of water that they're drinking, the vegetation that they're eating, what would be the highest expected concentration in the predominant food source and water, and you combine those two together to get exposure for something like a herbivore. And then for carnivores, you get what the exposure is or the estimated level in the animal is. And again, you always have it is always a conservative estimate as you're going through these steps. So no, it's not just one single exposure. You try and include all of them.
Yeah. Thank you. And the final question that I had was, you said that obviously this was soils study 18 sites to start with, and then the following work which you were involved in was on the wetlands. Are you still involved in that, or have you found major differences between the wetlands and the soils?
Yes. The issue is in the topography in the landscape. It's undulating. The uplands are rocky. There's limited soil. What you've got is soils accumulating in these wetland areas, and traditionally we think of wetlands as sinks for metals. But what we were finding is that actually they're becoming sources. So the metals accumulated in the peatlands, but because it's we get dry summers and we get droughts. The water table drops, the sulfur gets exposed. So in the fall, you get sulfuric acid, takes out the metal. So we're getting very, very high metal pulses in the fall. And we had 100 years of legacy of metals in these peatlands. So they were now converting from it, because emissions have gone down, they now became a source to the environment. Also, the sphagnum, that is key for the function of wetlands in terms of controlling water table and the ecology of these wetlands, are very sensitive to metals. So within about 10-kilometer area, no sphagnum. So we looked at, so if you went down about 2 centimeters in depth in the peatlands very close in, that peat is over 150 years old.
Yes.
No peat accumulation. If you go out 40 kilometers, then you've got, 1.5 foot for the same time period. So we weren't getting peat, so they weren't functioning the way they were. The vegetation was very different, and they're also acting as metal source. So right now, they're looking at ways in which you can ideally try and get sphagnum back on the landscape, because if we can control the water table, then we have less impact in terms of the droughts and that. But that's the challenge, and that's something that is the next step on this.
Yes, yeah. And I think similar situation in Scotland, although we don't have that contamination level, but getting the sphagnum re-established seems to be paramount to stopping these peatlands becoming a source of carbon. And we also have issues with phosphorus and things like that. Yeah. Do we have any more questions? I think we've stopped all the questions then for now. Thank you so much for that lecture today. And I would like to also say thank you to all the presenters. So we've had Shaun today, we've also had Sebastian Sobey from Montreal, Lina Ma from Florida, Rainer Schulen from ETH Zurich, Huan Zhong and Rongji from Nanjing, and Ian Oliver from Trent, from Keele University, sorry about that. So I do hope that everyone has enjoyed this course. So we've covered key soil concepts and soil contamination and remediation with a suite of case studies from around the world, and we've had an evaluation of risk assessment approaches and their application. Can I also thank Julia for placing all the information on the website and reminding us each week that lectures are coming up, and to Hui for being here every week, taking part in the sessions and for sorting out the problems as they arise, and to Doug for his support in running this course. So thank you very much, and I hope that you've enjoyed listening and that you've found it a worthwhile course. Thank you.
And I want to add my thanks, especially, first of all, to all the speakers, but especially to Margaret. It's trying to organize faculty schedules is kind of like herding cats. It's not an easy task. And to get everyone's schedules organized into a logical order that we had for this course was quite a challenge. So thank you, Margaret, for all your hard work. I've certainly enjoyed it, and I hope everyone else has enjoyed it as well.
Okay, thank you. Okay, final goodbyes then until July. Okay, right, bye.